Yeah, today we're happy to have Professor Satoshi Murai from Waseda University, and he's going to talk about hyperplane arrangement and their characteristic polynomials for the pre-seminar. The pre-seminar will be 3:30 to 4, and then the actual seminar will start at 4:10. Feel free to ask any question in the chat or just unmute yourself. Yeah, we'll hand over to the speaker.
Okay, thank you for the introduction and thank you for coming. And in my seminar talk, I will talk about the cohomology ring of regular nilpotent Hessenberg varieties and its connection to hyperplane arrangement. But in this pre-seminar, I just want to talk about some basic combinatorial things about hyperplane arrangement and in particular about the characteristic polynomials. So anyway, let's start. So let's start from what is a hyperplane arrangement. So this is a very simple combinatorial object. So a hyperplane arrangement is just a collection of hyperplanes. So if you consider the one-dimensional Euclidean space, then the hyperplane is just a point. So it's just a set of points on the line. And if you consider the hyperplane arrangement in the plane, then it's just a set of the lines. So here's some easy examples. So we have 1, 2, 3, 4, 5 lines in the plane, and this is a this is actually a line arrangement. And if you go to the dimension 3, then you have a collection of the collection of the planes. And these are very basic combinatorial objects. And in particular, so if we consider the hyperplane arrangement, one of the most important combinatorial invariant is the polynomial, which is called the characteristic polynomial. And in this talk, I want to explain mainly about what is a characteristic polynomial. And actually, this talk is very basic, so I'm sorry that I know that some expert is here, so for the expert, this may be boring. And anyway, so let me first define what is a characteristic polynomial. And to define this polynomial, I actually need some preparations. So to explain this, so I need two things. So one thing is the intersection poset, or sometimes people also call it intersection lattice. And the other thing is a Mavis function. So let me first introduce intersection poset. An intersection poset is actually a set of affine space, which is obtained as an intersection of hyperplanes in the arrangement. So formally, we take a subset of the arrangement, then consider the intersection, and take all the subset of them, then all the set, take the set of all these things, then you get the intersection poset. And I just want to explain this in the picture. So if we consider the arrangement in R2, then the affine space, which is obtained by intersection of hyperplane, is just lines and points. So in this picture, we have, so the arrangement are just these 5 lines. And then as an intersection of hyperplanes, you get 4 points. But for some technical reason, I want to assume that the whole space is also contained in the intersection poset. So in this case, the intersection poset consists of these 1, 2, 3, 4, 5 lines, and these 4 points, and the whole space R2. And this is a poset with respect to the inclusion. And when we consider intersection poset, we order the elements by the reverse inclusion. And so here is a Hasse diagram of the intersection lattice. So in so because we consider the reverse ordering, we have a bottom element which must be equal to the whole space itself. And then we have 1, 2, 3, 4, 5 lines. And we also have 4 points, A, B, C, D, which is these 4 points. And the relation is obtained by follow. So as I said, the R2 is the smallest element. Then in the next we have these 5 lines. Then, for example, consider this point A. The point A is this point. This point is contained in the line 3 and line 1. So we have a relation between the 1 and 3. So this point A is this point, and this is contained in line 1 and line 3, so we have a relation like that. And if we consider the point B, then this point B is contained in line 2, 3, 5. So we have a relation to 2, 3, 5. And I don't think I need to continue, but just in case. So if we have consider the point 3, then this is contained in line 1, 4, 5. So we have a relation to 1, 4, 5. So anyway, so this is the intersection process. So consider all affine space, which is obtained by the intersection of the hyperplanes. And then we consider the ordering, which is defined by the reverse inclusion. And then we regard it as a poset. Okay, is that okay for the moment?
Just out of curiosity, why
Yes.
don't we, do you know why we don't include the empty set?
Yeah. I mean, it's just a technical reason, so it doesn't really important to consider the important empty set. Actually, you're right. It's just not important for in this case. Any other question? Okay, so then next let me define the Mavis function. So I actually just defined the simplified version of the Mavis function. So I want to define that Mavis function is a function from the intersection poset to the set of integers. And the Mavis function is defined somewhat inductively. So first, I define that Mavis function of the bottom element, which is equal to the whole space, is equal to 1. And then we define the Mavis function of affine space X is equal to the minus 1 times sum of the Mavis function of the element Y, which is between X and Rn. So actually, Y properly contains X and which is subset of Rn. This is the definition, but so this actually it is more convenient to consider that this is defined by this relation. So I mean, so if we consider all the affine space which is in between X and Rn, and if it takes the sum of the Mavis function, then it must be 0. And I think you need some time to get used to these kinds of objects. So let me explain this again by example. So if we consider this arrangement, then as I said, so the Hasse diagram of this poset is this poset. And then the Mavis function defines something like as follows. So first, we put the Mavis function is a function from the intersection poset to integers. So it just assigns numbers to each element of the intersection lattice, intersection poset. And the way we put the numbers the following. So first, we put 1 to the bottom element. The bottom element is, in this case, it's just R2. And then we put -1 to the elements above the bottom. So this is because of this condition. So this condition says that if we consider this element, so suppose that this element is x, and this condition says that if we consider the element which is below x, then, so in this case, so the only element which is smaller than x is just R2. And then the condition says that some of these two elements are 0. And because we already put 1 in the bottom element, so this element x must have a value -1. And similarly, so for these elements, we get the value -1. And then we continue this procedure. And for example, if we consider this element, then this definition says that the sum of the values of the Mavis function of these 4 elements must be equal to, maybe I shouldn't circle. The sum of these 4 elements, Mavis function of these 4 elements must be equal to 0. So this means that we must have 1 in here. And okay, and if we consider this element, so by this definition, so we must, so this, if we consider these 1, 2, 3, 4, 5 elements, then the sum of the Mavis function must be equal to 0. And because we have 3 minus 1 and 1 plus 1, if we, the value of Mavis function of this element should be 2. And similarly, if we consider the Mavis function of this element, then this, so the sum of the Mavis function of these 4 elements must be equal to 0. So this must be 2. And finally, if we consider the value of the Mavis function here, then we get, we get 1 by the same rule. And maybe I just point out that in this case, the Mavis function is somewhat determined by somewhat simple rule. So we have the value 1 and the value 2 for the points, but the value, the points which has Mavis function 2 is exactly the vertex B and C. The vertex B and C is just the intersection of 3 lines. And the points which has value 1 as points A and D. So A and D are just points which are intersection of 2 lines. So this, in some sense, in this case, this somewhat Mavis function considers the multiplicity of the intersection of the lines. And this is not, I mean, this is this is a very simple case, and the Mavis function of more general hyperplane arrangement is more complicated, but so it gives some intuitive understandings. And is there any question at this moment?
Yeah, I have a question. So it looks like this Mobius function can be defined on any poset with a minimal or maximal element.
Yes, exactly. So I just explained the special case of the intersection poset, and you're completely right.
Is this related to the Mobius function on the integers? Is that the same?
Oh, yes. It comes from the Mavis function of integers. Yes, exactly.
Okay, thanks.
Okay, then now let me define the characteristic polynomial. So let A be a hyperplane arrangement in n-dimensional Euclidean space. Then the characteristic polynomial defined as a polynomial in T as follows. So it is the sum of the Mavis function times T to the dimension. And here, X runs over all elements of the intersection poset. So maybe again, I explain this by example. So, and I already write the intersection example of the intersection poset and the value of the Mavis function. And then the characteristic polynomial is obtained as follows. So first, recall that so this element is a two-dimensional Euclidean, two-dimensional affine space, and these 5 elements is a affine space of dimension 1, and these 4 elements correspond to the point, so it is a zero-dimensional affine space. Then, so for each Mavis, for each these elements, so for the two-dimensional one, we put t to the square, and then for each element of dimension 1, we put t. And for the points, which is a zero-dimensional affine space, we put t to the 0. So it's just a, maybe I should write, maybe I write t to the 0, which is just equal to 1, but just in case, maybe it's easier to understand if I write. And so I just put t to the dimension into each element. And then just take a sum of these things. So in this case, we have, if we take a sum of these things, we have t squared first, and then here we have 5 minus t, and then we have 1 plus 2 plus 2 plus 1. So the whole polynomial is something like this. So t plus minus 5 times minus t, and 1 plus 2 plus 2 plus 1, and which is equal to t squared minus 5t plus 6. And this is a characteristic polynomial. So we first compute the Mavis function of these each element, and then we add the t to the dimension, and then take a sum of these elements. Then you get a characteristic polynomial. So this is the definition of the characteristic polynomial, and probably I should explain why this characteristic polynomial is interesting. And this characteristic polynomial is interesting because this contains many interesting combinatorial informations. And I want to introduce 2 basic results about this topic. And the first thing is what people call the Zaslavsky's theorem. So Zaslavsky's theorem says the following. So let A be a hyperplane arrangement and consider its characteristic polynomial. Zaslavsky's theorem says that if we substitute t is equal to -1 to the characteristic polynomial, then you will get the number of the regions of the hyperplane arrangement. So actually, this is the first statement which I write. So if we substitute t equal to -1 to the characteristic polynomial, then you get the number of the regions in the hyperplane arrangement. And I don't really explain what is the assumption, but in some appropriate assumption, if you substitute characteristic polynomial to t is equal to 1, then you actually get the number of the bounded regions. So again, let me explain this by example. So in this hyperplane arrangement, the region is a connected component in this picture. So for example, so this is one region, and this is another region. And this triangle is also one region. If you count, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You have 12 regions. And for the bounded region, so this triangle is a bounded region. And you have another bounded region here. And you have 2 bounded regions here. And I already computed the characteristic polynomial of this arrangement, which is equal to t squared minus 5t plus 6. And if you substitute t is equal to -1 in this polynomial, you get 1 plus 5 plus 6, and this is equal to 12. And if you substitute t is equal to 1, then you get 1 minus 5 plus 6, which is equal to 2. And these are exactly the number of the regions, and also the number of the bounded regions. So this is somewhat surprising result. So if we consider characteristic polynomial, and if we substitute it is equal to 1 or minus 1, you get something nice, very nice combinatorial information. And this is one very nice result about the characteristic polynomial. And I actually want to introduce one more combinatorial result about characteristic polynomial. So the other result is about the coloring of the graphs. So, okay, let's consider the simple graph. Simple graph means that a graph without loops and without multiple edges. And let's give a simple graph with vertex set B. Then, so in the graph theory, it is sometimes very important to consider the coloring of the graphs. And I want to say that a proper coloring of the graph is a map from the vertex set of the graph to the set of integers 1 to k, satisfying that ck is not equal to cv whenever xy is an edge of g. So I define the coloring as a map, but you can actually consider that this map is something like putting colors in each vertices. And the condition says that if we have two vertices which are adjacent, then they must have the different color. So for example, this is the example of the proper coloring. So if we put red color in these vertices, and if we put blue color here and green color here, then this is a proper coloring because each adjacent vertices have a different color. But this coloring is not a proper coloring because so I put the red color in these vertices, but these two vertices are adjacent, so this is not allowed. And about the coloring, so I actually consider the numbers of the coloring of the numbers of these proper k colorings. And the counting function of the number of the proper coloring is called the chromatic polynomial. So formally, so chromatic polynomial, so let me denote this by chi gt, is a function which is defined by xgk to be equal to the number of the proper k coloring of g. So this chi g just counts the number of coloring k coloring of g. And I say that this is a function, but it is known that this becomes a polynomial in k. So this is usually called chromatic polynomial. So here is some example. So consider this graph G. Then, so first, there is no way to color these two, but color the vertices of this graph using only two colors. So you get chi G2 is equal to 0. And for chi G3, so you consider the coloring of the vertices of this graph with using 3 colors. And actually, there is essentially one way to color these vertices. So one way means that so if you put a color 1 in the vertex 1, and then you must color the vertex. You must, and suppose that you color the vertex 2 by 2, then you automatically get that. So the coloring of the vertex V3 must be 3, and you automatically get that the vertex coloring of the vertex V4 is equal to 1. So we essentially have one way of the coloring of this graph. And but actually you have some I'm sorry, I just this. You have some permutations of these colorings, and you actually totally get the 12 coloring of the 12 3 colorings. And it's not easy to count the number of the 4 coloring, but it is equal to 72. And actually, probably you need some time to think about it, but you consider the number of the proper n coloring, you get the number n times n minus 1 times n minus 2 times n minus 2. So this is because, so this can be computed as follows. So first, so if we want to color the vertex V1, then you have n choice of the colors. Then for the B2, you cannot use the color which you used for B1. So you have n minus 1 choice of the color for B2. And then if you put colors to B3, then it cannot be the same as the colors of B1 and B2. So you have n minus 1, 2 choices for vertex B3. And then for B4, so you cannot put colors which you used for B2 and B3. So you have n minus 2 choice. And the number of coloring is in this case, so it's just a sum of the choices. So n times n minus 1 times n minus 2 times n minus 2. So and this is actually a simple, very simple example, and you cannot always compute the number of the colorings in this way. But so in this case, you can do it. And about the I introduced the chromatic polynomial. But actually, it is known that chromatic polynomial is a special case of the characteristic polynomial arrangement. So I just introduced a theorem and I will finish soon. So let G be a simple graph whose vertex set are B1 to Bn. And let Hij be the hyperplane defined by xi minus xj is equal to 0. And let Hg be the hyperplane arrangement whose elements are the Hij such that Bivj is the edge of the graph G. Then it is known that the characteristic polynomial arrangement is equal to the chromatic polynomial of the graph. This is a kind of a very surprising result because the two definitions of these polynomials are very different. But so this also shows that the characteristic polynomial arrangement actually contains a chromatic polynomial graph. And chromatic polynomial graph itself is a very interesting object to study, and it's a very special case of the characteristic polynomial arrangement. And as a simple application of this theorem, you can actually compute the characteristic polynomial of what people call the braid arrangement. So braid arrangement is just a hyperplane arrangement consisting of all Hij. But this arrangement is just actually equal to the chromatic polynomial complete graph. So you can easily compute the characteristic polynomial by counting the number of the coloring. Although it is not so easy to compute the intersection lattice, you can compute the characteristic polynomial arrangement. And I'm sorry, so I'll stop here. And so in this talk, I explained some combinatorial result about the characteristic polynomial. But so this characteristic polynomial actually has an algebraic aspect. So in the seminar talk, I will talk more about some algebraic side of the story. Okay, sorry, I'm a bit late, but any questions?
Just to confirm, a simple graph is like a graph, not a hypergraph, or I mean, not a multigraph.
A simple graph is just a graph, not a hypergraph, and they don't have multiple edges or loops.
And no loops, right?
No loops, yeah.
Are there any questions? Other questions? If there's no more questions, let's all thank the speaker for the really nice pre-seminar. You can either clap your hands or click on the clapping reaction.